Hello, calculus fans, and welcome back. Today's lecture is on improper integrals, section 9.4. Please notice that we actually are skipping 9.3, one of the very few sections that we skip. And so we begin with talking about the definition of what an improper integral is. Okay, so an integral that has infinity as one of its limits of integration is known as an improper integral, and we have three cases to look at. The first one is we assume that f is continuous on the interval a to infinity. Then this integral is equal to the limit as b approaches infinity of the integral from a to b of f of x dx. So we take that improper integral and we express it as a regular integral, and we have a limit in there. And the same thing here. This limit is going to be, this improper integral will be the limit as a approaches negative infinity of the limit as a approaches negative infinity of the integral a to b of f of x dx. And finally, this last one, the integral from minus infinity to infinity of f of x dx is equal to the integral from minus infinity to c of f of x dx plus the integral from c to infinity of f of x dx for any real value c. And what we notice is that this expression is evaluated by part 2, and this expression is evaluated by part 1. And so that takes care of these ideas of improper integrals. And then we'll look, of course, at how they work. Okay, so in passing, we should talk about some language. So if we have a limit like this, and if that limit does indeed exist, then we say that that improper integral converges. If the limit doesn't exist, then we say that that improper integral diverges. And so those two words, converge and diverge, are important ones, and you should have a feeling for how we use them. Okay, so let's take a look at this classic improper integral. So we're looking at the function y equals 1 over x, and we want to look at the area under that, essentially, from 1 out to infinity. Now, most people would say, okay, that area is infinite. And in fact, if we go ahead and we write this as the limit as b approaches infinity of the integral of 1 over x, which is the ln of x, from 1 to b, we get the limit as b approaches infinity of the ln of b minus the ln of 1. Now, we know that the ln of 1 is 0. And so therefore, this limit then is just equal to ln of b as b goes to infinity. And in fact, it goes to infinity, so that we say that this improper integral diverges, and also that this area is infinite. Nothing surprising there. Okay, well, so let's look at this one. It's almost the same. I mean, the graph is very similar. You know, when you graph 1 over x squared or 1 over x in the first quadrant, it's, pretty impossible to know which is which, unless they're both graphed on the same set of axes. And so we want to get some idea of what this area is, or what this improper integral is. All right, so it's the limit as b approaches infinity of the integral of that, which is minus 1 over x from 1 to b. And that equals the limit as b approaches infinity of minus 1 over b minus 1 over 1. which is the limit as b approaches infinity of 1 minus 1 over b. And as b approaches infinity, we know that 1 over b goes to 0, and so this limit is equal to 1. Unbelievable that that so-called infinite area not only converges, but is actually equal to a very small number, 1. So this is one of those just, I think, amazing results. And graphically, the graphs look the same, the areas look similar. One area is infinite, the other area is equal to 1. Go figure. Gotta love math. Okay, so let's check this one out. Here we're looking for the area from minus infinity to infinity under the curve 1 over 1 plus x squared. Well, what's that going to be? At this point, your intuition probably just says, I don't know, I got to do the work. So, using our rule for this, we're going to write this as the integral from minus infinity, and we'll pick any number, and 0 is obviously the most convenient number. 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. And so this is equal to the limit as a approaches minus infinity of the arctan of x from a to 0. And then the next one will be the limit as b approaches infinity of arctan of x from 0 to b. That's a 0. Alright, so let me, at the risk of kind of losing out on some space, let me graph arctan of x. Okay, so this asymptote here is pi over 2, and this asymptote down here is minus pi over 2. And so what we get here, just let you figure it out a little bit, the arctan of 0 is 0. This should be a 0, right? Up there. So this is going to be pi over 2 plus pi over 2, and so this area is equal to pi. Wow, where did that come from? No one saw that one coming. So, fill in any missing steps that you need, but very, very cool how that works. So now take a look at this one. Just a cursory glance, and you'd say, well, that's not an improper integral. But what you have to notice is that 1 over x minus 2 is discontinuous at x equals 2. In fact, approaches infinity. And so this is indeed an improper integral. And so we need to rewrite it like this. The limit as c approaches 2 from the left of that integral, which is the ln of x minus 2, from 1 to c. And so that can be written as the limit as c approaches 2 from the left of the ln of c minus 2 minus the ln of 1. And once again, it pops up. We got the ln of 1, and we know that that's 0. And so this is just equal to the ln of c minus 2 as c approaches 2 from the left, which means this thing is approaching 0. And so this is, well, going to be approaching negative infinity, which means that our original improper integral diverges. Alrighty? So the last thing to discuss in Chapter 9 is what's called the comparison test for improper integrals. And so we make this assumption that as long as x is greater than or equal to a, f of x is greater than or equal to 0 and less than or equal to g of x. Then there's two parts. This first improper integral converges if this improper integral converges. Makes a lot of sense, right? And similarly, the next improper integral right here, this will diverge if the integral from a to infinity of f of x dx diverges. So those are pretty easy to understand. Being greater than or equal to 0 is an important piece too. So believe it or not, that concludes Chapter 9, and Chapter 10 is coming up. And Chapter 10 is probably the real key of BC calculus, and you're going to love it. It's going to be tough, but you'll love it. Lots of cool results coming. So see you soon.